Hello everyone. So in this video we continue with chapter 5, trigonometric functions and equations, specifically section 5.4, trigonometric equations and identities. We are going to take a look at the unit circle and exact solutions to trigonometric equations. So let's look at example 5.12, and it says find the exact solution or solutions to the equation sine of x equals 1/2 for a domain between 0 and 2 pi, not including 2 pi, but including 0. So if we have that sine of x is equal to 1/2, we can reference the triangle that has 1 for the opposite of this angle here, 2 for the hypotenuse, and recall that square root of 3 for this other side. And this is the 60-30 right triangle, the special right triangle. So this here, in terms of radians, because notice that they want an answer in radians, is pi over 6. So sine of pi over 6 is equal to 1/2, opposite over hypotenuse. Now this, of course, would be pi over 3. So if they were asking for cosine, we would know it would be pi thirds. Now we have to use the unit circle as a reference, of course, in these cases. And let's recall that sine in the unit circle is represented by the y-coordinate of the angles. So we have two solutions. Why? Well, because sine is positive here, right? Here we have that cosine is positive, sine is positive. Here we have that cosine is negative and sine is positive. So we have two possible solutions within this domain. And those solutions are going to be pi over 6, which we found with the reference triangle, but we cannot forget the other solution, which is 5 pi over 6. So we say that x is equal to pi over 6 and also 5 pi over 6. So now let's take a look at example 5.13, and it says find the exact solution or solutions to the equation tangent of theta plus 1 equals 0 for an angle theta between 0 and 360 degrees, not including 360 degrees. So notice that here they want the answer in degrees. So tangent of theta plus 1 equals 0 can be rearranged as tangent of theta is equal to -1. Let's recall that there's an identity that says the tangent of an angle is equal to the sine of that angle divided by the cosine of the angle. And then the reference triangle, the special right triangle for this case, is going to be the triangle where we have 1, 1, and the hypotenuse with a measurement of square root of 2. So we know that this is going to be the 45, 45 special right triangle. This is 45 degrees as well. And then we know that sine of 45 is equal to 1 over square root of 2. And we also know that cosine of 45 is also equal to 1 over square root of 2. Therefore, tangent of 45 is equal to 1 over the square root of 2 divided by 1 over the square root of 2, which gives us 1. But we know that there are cases where we're going to have that sine is negative or cosine is negative. We need these to be opposite in sine in order to get -1. So if we go back to the unit circle, we know that in the first quadrant, cosine is positive and sine is positive. Therefore, there's no solution in the first quadrant. But there would be a solution in the second quadrant because here we have that cosine is negative and sine is positive. There's no solution in the third quadrant because here both are negative. But there is another solution in the fourth quadrant where cosine is positive and sine is negative. So our reference angle of 45 means that I have a solution here and another solution here. And we know, if we go back to the unit circle, that both solutions are going to be 135 degrees, which is in the second quadrant, and 315 degrees, which is in the fourth quadrant. Therefore, x is equal to 135 degrees, and x is equal to 315 degrees. So now let's take a look at example 5.14, and they ask us to find the exact solution or solutions to the equation cosine squared of x minus pi thirds is equal to 1/2 for an x between 0 including 0 and 2 pi not including 2 pi. So they want the answer in radians. Okay, so here the first thing to notice, and this is sometimes confusing, cosine squared of x minus pi thirds is the same as saying cosine of x minus pi thirds squared. So it's the whole thing that is squared, not just this little part. And then we have that this equals 1/2. Therefore, we can find a solution by square rooting both sides, and we get that cosine of x minus pi thirds is equal to plus minus. Remember that we have to use plus and minus when we square root. So this is going to be plus minus the square root of 1/2, which is the same as plus minus 1 over square root of 2. So that means that our reference triangle, or our reference angle, I should say, is 45 degrees. In other words, if we go to the unit circle, we would have that this would be a reference angle, 45 degrees, or pi fourths, and then we would have 3 pi fourths, 5 pi fourths, and then 7 pi fourths. Now notice that these are not the solutions yet, right? Because we have a horizontal shift. Notice that we have that x minus pi thirds is going to be what is equal to these angles. So we have to be very careful about that. Now notice also that there's a distance of pi halves between these. In general, we can say that the solution for this problem is going to be in the form x minus pi thirds is equal to pi fourths plus some k times pi halves. Why k times pi halves? Well, k is just going to be an integer. And what this is going to give us is the fact that there's a distance of pi halves between all the solutions. So we could rewrite this as x, let's do it over here, x equals pi fourths plus pi thirds, which is going to be 7 pi over 12, really, 7 pi over 12. That's from adding this to this, 7 pi over 12 plus k times something in the form of 6 pi over 12. Notice that this is the same as saying pi halves, but I want to have the same denominator in order to be able to add them easily. So we would say for k equals 0, we would have that x is equal to 7 pi twelfths. For k equals 1, we would have that x equals 7 pi twelfths plus 6 pi twelfths, which is going to be 13 pi over 12. for k equals 2, x would equal 7 pi twelfths plus 12 pi twelfths, which is going to be 19 pi over 12. And notice that all these answers are still within the domain for x because they are greater than 0, but still less than 2 pi. But if we use k equals 3, we would get that x is equal to 7 pi over 12 plus 6 times 3, 18, so 18 pi over 12. And if we add these, this is going to be 25 pi over 12. But this is obviously greater than 2 pi. So this is not a solution. Now, this doesn't mean that we found all the solutions because we could also have a negative value for k. So let's test k equals -1. In the case of k equals -1, we would see that x is equal to 7 pi over 12 minus 6 pi over 12, which is pi over 12. And if we use -2, it would give us a negative result, which is not in the domain because the minimum value for the domain is 0. So therefore, we have all solutions. X is equal to pi over 12, 7 pi over 12, 13 pi over 12, and 19 pi over 12. So now let's take a look at graphical solutions to trigonometric equations. Now by graphical, they mean using the GDC. If exact solutions are not required, then a graphical solution using your GDC is a very effective way to find approximate solutions to trigonometric equations. Unless instructed to do otherwise, you should give approximate solutions to an accuracy of 3 significant figures. So if we take a look at example 5.15, it says, find the solution or solutions to the equation 1 plus tangent of x equals 0 for the interval between -pi and pi, not including pi. So we could rearrange this and make it tangent of x is equal to -1, but that's unnecessary. We'll just go straight to the GDC. So what we want to do here is go to y equals and simply enter the function 1 plus tangent of x. And then before we graph it, we want to make sure that we have the appropriate window. So it would be from -pi to pi. And then because it's a tangent function, we can leave the standard y minimum and y maximum. So now we hit graph. And notice that we have two solutions because there's two instances where the function is equal to 0. And we can find these by going second, calculate, and option number 2, 0. So notice that it asks again for the left bound. So we need to move this below the x-axis for the left bound, and then above the x-axis for the right bound. Hit enter, guess, and there's our first solution. So notice that they say that we have to write the answer with an accuracy of 3 significant figures. So we would have to write this as -0.785. Let's look for the second solution. So we go second, calculate, 0. And let's move it to the other intersection. So notice that we're going to go right. That's just going to take us up and then back from below. So that's going to be the left bound, enter, right bound, we have to go above that intercept, enter, guess, and there it is. We would then have that x is equal to negative 0.785 and to 2.36 rounded to three significant figures. So now let's continue with example 5.16. And it says, the peak height h meters of ocean waves during a storm is given by the equation h equals 9 plus 4 times sine of t halves, where t is the number of hours after midnight. An alarm is triggered when the peak height goes above 12.5 meters. Find the value of t when the alarm first sounds. Okay, so for this, we're going to use the GDC. So we need to go to y equals, and we enter the first equation, or the first function, 9 plus 4 sine of x divided by 2, but also we need to enter the equation for 12.5 meters, which is going to be a horizontal line. 12.5. Okay, but before we hit the graph button, we need to make sure we have the right window. So because the equation represents the number of hours for the x-axis after midnight, we could start at 0 and then 24 for a total of 24 hours. And then for y, notice that the minimum for this function is going to be 5 because 9 minus 4 is 5. When sine is negative 1, it'll be the lowest. But we can just start from 0, and then we need a maximum height that is above the 12.5 meters. So let's say 15. Now let's graph. So that's the sine function. And now comes a line representing 12.5 meters. So we need to find that first intersection between the sine function and the line, which is going to give us the answer. So we need to go second, calculate, and now 5 intersect. So first curve, now we need to be careful because we need to be close to the actual intersect. So that's the first curve. Hit enter. Second curve, notice that it moved to the line. Hit enter again. Guess. And there it is. So t is going to equal 2.13 hours. And that's to three significant figures. So next we're going to take a look at analytical solutions to trigonometric equations. Now analytical solutions means using methods of algebra. And let's take a look at example 5.17, which says solve 2 sine squared of x plus sine of x is equal to 0 for the interval between 0 and 2 pi, but not including 2 pi. So some people prefer to use a substitution. So we can say let sine of x equal y, and then we can rewrite this equation as 2y squared plus y is equal to 0. And then we can rearrange it. We always want to factor. So here we can have a factorization by means of common factor. So y times 2y plus 1 is equal to 0. Therefore, y is equal to 0, or 2y plus 1 is equal to 0, which means that y is equal to negative 1/2. So in other words, sine of x is equal to 0, or sine of x is equal to negative 1/2. So if we go to the unit circle, let's suppose this is a unit circle, we know that sine is 0 here at angle 0 because the coordinate for this is 1, 0. Therefore, sine is 0 when x is equal to 0. And also here, because the coordinate is minus 1, 0. So that means that x can also equal pi. And then sine of x equals 1/2 or negative 1/2. Our reference triangle is going to be the one where we have that sine is 1 over 2, and then cosine is square root of 3 over 2 for this angle, which is 30 degrees or pi over 6. This is the 30-60 special right triangle. Remember that this here would be pi over 3. So we know that sine of pi over 6 is equal to 1/2. But then sine has to be negative 1/2. And that's going to occur in the third and fourth quadrants. And here we know that this angle here is going to be 7 pi over 6. And this other angle here is going to be 11 pi over 6. Therefore, our solutions for x are going to be 0, pi, 7 pi over 6, and 11 pi over 6. So now we'll continue with example 5.18, and it says solve 3 sine of x plus tangent of x is equal to 0 for x between 0 and 2 pi, including both 0 and 2 pi. So we have to be careful with this here. Now, the recommendation in these cases where you have tangent is to rewrite it in terms of sine and cosine. So we can have this equation written as 3 sine of x plus sine of x over cosine of x is equal to 0. Then we want to get rid of this cosine of x that is dividing, and we can do that by multiplying both sides of the equation by cosine of x. So we would get 3 sine of x times cosine of x plus sine of x is equal to 0. And then we don't really need to do a substitution. We can just factor out sine of x. And notice that we can write this as sine of x times 3 cosine of x plus 1 is equal to 0. Therefore, sine of x is equal to 0, or cosine of x is equal to negative 1/3. So here we know the solutions from the previous example. We know that x can equal 0, it can also equal pi, but then also 2 pi, because 2 pi is in the domain. Now for this second part, cosine of x is equal to negative 1/3, we cannot really use the unit circle. So we'll have to use a GDC. We need to go to y equals and plug in cosine of x as well as the line negative 1/3. And then we have to make sure that we have the right window. So the domain is from 0 to 2 pi. So let's write 0 and 2 pi. Okay, and then for the y minimum, we know that cosine fluctuates between -1 and 1, but we want something a little bit bigger than that. We can say -2 and 2. And now we can graph, and there's the cosine function, and there goes the line that represents -1/3. So we would have to find those two intersections. We go second, calculate, and number 5, intersect. First curve, let's get close to that first intersect. First curve, second curve, guess. And there is our first solution. So let's write that down. We have that for here, x is equal to 1.91 to 3 significant figures. And now we go and find the second solution. Number 5, intersect. So first curve, let's move close to the other intersection. First curve, hit enter. Second curve, hit enter. Guess. And there is the other solution, which is going to be 4.37 to 3 significant figures. On the next slide, you're going to find a summary of trigonometric identities. And these identities are very handy when you want to solve trigonometric equations. The first one is the definition of the tangent function, where, as we said before, tangent of x is equal to sine of x over cosine of x. We have the cofunction identities, where sine of pi halves minus x is equal to cosine of x, and cosine of pi halves minus x is equal to sine of x. Then we have the Pythagorean identities. These are derived from the unit circle. Sine squared of x plus cosine squared of x is equal to 1. And then these two that are simply rearrangements of the first one. So sine squared of x is equal to 1 minus cosine squared of x, and cosine squared of x is equal to 1 minus sine squared of x. Finally, we have the double angle identities. There's only one for sine, which is sine of 2x is equal to 2 times sine of x cosine of x. And then we have 3 from which to choose for cosine of 2x. We have cosine squared of x minus sine squared of x. Then we have that cosine of 2x is also equal to 2 times cosine squared of x minus 1. And it is also equal to 1 minus 2 sine squared of x. So now let's take a look at example 5.19, and it says solve the equation cosine of 2x plus cosine of x is equal to 0 for the interval between 0 and 2 pi, including 0 and 2 pi. So notice that we have a double angle. So we can use the double angle identities for cosine of 2x, which we know are going to be cosine squared of x minus sine squared of x, which is also equal to 2 times cosine squared of x minus 1, and this is equal to 1 minus 2 times sine squared of x. So we can use either one of these three because they are equivalent. But this one here is the more convenient one. Why? Because we want to leave this equation only in terms of cosine of x. So then we can rewrite this as 2 times cosine squared of x minus 1 plus cosine of x is equal to 0. And then if we do a substitution, although it's not necessary, sometimes it's more comfortable, let y equal cosine of x, we can rewrite this as 2y squared, and I'm going to rearrange a little bit, plus y minus 1 is equal to 0. And then here we can do a factorization by inspection. So notice that 2y times y is 2y squared. And then 1 times negative 1. And notice that if we multiply y times negative 1, that's minus y. And 2y times 1, that's 2y. If we add them, we're going to get plus y. That means that we can rewrite this as 2y minus 1 times y plus 1 is equal to 0. Therefore, y is equal to 1/2 or y is equal to negative 1. But in reality, we're solving for cosine. So that means that cosine of x is equal to 1/2 or cosine of x is equal to negative 1. So these two we can solve manually because we do have the unit circle as a reference for these. So 1/2 cosine of x is equal to 1/2. Our reference angle here is going to be 60 degrees or pi thirds. That's our reference angle. So we need to know where cosine is positive in the unit circle. And we know that cosine is positive in the first and fourth quadrants. So because the solutions are between 0 and 2 pi, that means that our solutions have to be pi thirds, and the other one would be 5 pi thirds, which is in the fourth quadrant. Cosine of x is equal to negative 1. Now think of the unit circle again, and remember that it intersects here at this point with the x-axis, and the coordinates here are -1, 0. So that means that cosine of pi is equal to negative 1. And that's the only solution there is in that interval. So that means that x is equal to pi thirds, pi, and 5 pi thirds. So let's continue with example 5.20. And for part A, it says express 2 times cosine squared of x plus sine of x in terms of sine of x only. So 2 times cosine squared of x plus sine of x in terms of sine of x only. So we need to use the identity from the Pythagorean identities that says that cosine squared of x is equal to 1 minus sine squared of x. And then we can substitute. So then we would have to be careful here because there's a 2 multiplying cosine squared. So we have to go this equals 2 times 1 minus sine squared of x plus sine of x. And this is going to equal 2 minus 2 sine squared of x plus sine of x. Now for part B, they want us to solve this equation over here. But notice that the left-hand side is the same as this. So I'm going to erase, and we're going to solve for part B. So for part B, they want us to solve for this equation. But like I said, it's equivalent to the expression that we found before, at least the left-hand side, right? So 2 minus 2 sine squared of x plus sine of x is equal to negative 1. We can rearrange this, and we can write it as minus 2 sine squared of x plus sine of x plus 2 is equal to negative 1. And then we can bring the negative 1 to the left-hand side. So we could write this as minus 2 sine squared of x plus sine of x plus 3 is equal to 0. And then finally, if we multiply both sides by negative 1, to get rid of this negative sign up here, we would get 2 sine squared of x minus sine of x minus 3 is equal to 0. Then if you prefer, we can do a substitution. We can say let sine of x equal y, and we can rewrite this expression or equation as 2y squared minus y minus 3 is equal to 0. So this allows us to do a factorization. We'll do it through inspection. So notice that this is the same as saying 2y times y, and then with negative 3, we can write it as 1 times negative 3. This is convenient because if we now multiply 2y times 1, that gives us 2y. And if we multiply y times negative 3, that's negative 3y. And if we add them, we get negative y in the middle, which is what we want. So that means that this is equivalent to 2y minus 3 times y plus 1 is equal to 0. Therefore, y is equal to 3/2, or y is equal to negative 1. But we're not solving for y, we're solving for sine of x. So that means that we have to solve for sine of x is equal to 3/2, or sine of x is equal to negative 1. Now, this one has no solution because sine is a function that is between negative 1 and 1 at the most. And this is obviously greater than 1. Therefore, this is not solvable. And then sine of x equals negative 1 in this interval between 0 and 2 pi, including 0 and 2 pi, we know there's only one solution. And if you think of it, it's going to be over here, where the coordinate of that intersection is 0, negative 1. And that's for x equals 3 pi halves, which is the only solution for the equation. So we continue with example 5.21, and it says solve the equation 2 times sine of 2x is equal to 3 cosine of x for the interval between 0 and pi, including 0 and pi. So here, we need to use the double angle identity for sine. So we know that sine of 2x is equal to 2 times sine of x cosine of x. So we can substitute that into the equation, and we're going to get 2 times 2 sine of x cosine of x is equal to 3 times cosine of x. And then we multiply this on the left-hand side, and this is going to be 4 times sine of x cosine of x is equal to 3 times cosine of x. Now, one common mistake is the temptation to cancel out cosine. Because we have cosine on both sides of the equation, then we think we can just cancel it out using the algebraic properties of dividing with the same value on both sides of an equation. But when we're solving trigonometric functions, we don't want to do that because we might actually cancel out a valid solution. What we really want to do is always bring all terms to the left-hand side. So this can be written as 4 sine of x cosine of x minus 3 cosine of x is equal to 0. And then we want to factorize. So notice that cosine of x is actually a common factor. So we can say cosine of x times 4 sine of x minus 3 is equal to 0. And then we have that cosine of x is equal to 0, or sine of x is equal to 3/4. Now this one is easy to solve because we know that cosine of x is equal to 0 in this interval at x equals pi halves. Why? Well, if you think of the unit circle, this coordinate here would be 1, comma 0, and this coordinate here is 0, comma 1. So for this coordinate at pi halves, cosine is equal to 0. So this would be the solution for cosine of x is equal to 0 in that interval for 0 and pi, right? X is between 0 and pi, including 0 and pi. And then for this other one, we can't really reference the unit circle, so we will have to use technology. So we need to go, as in the previous examples, to y equals, and we plug in sine of x, and we also need to plug in y equals 3/4, which is the line. And then we need to make sure the window is appropriate. So x is the domain, and it goes from 0 to pi. So let's write 0 and pi. And then for y, because it's the sine function, we know that it is always between -1 and 1, but we want it to be a little bit larger, so let's use -2 and 2. And let's hit graph. And it looks like there's two solutions in that interval. So once again, we go to second, calculate, option 5, intersect. First curve, let's make sure that we're close to the first intersection. So enter, first curve, enter, second curve, enter, guess, and there's the intersection. So that's our first solution for x. In the case of sine of x is equal to 3/4. So let's write it down. We'd say that x is equal to 0.848 to 3 significant figures. And now let's proceed to find the second solution. So we need to go again, second, calculate, intersect. But now we need to move the cursor to a place closer to the other intersection. So there we are. First curve, enter. Second curve, enter. Guess. And there's the solution. So it's going to be at 2, comma, or 2.29. So those would be the three solutions for this equation. And now we're going to do example 5.22, which will be the last one on this video. And it says, given that cosine of x is equal to 1/4, and that the domain for x is between 0 and pi halves, find the exact values of part A, sine of x. So for part A, there's two different methods that I'm going to show you. The first one is using the fact that cosine of x is equal to 1/4, then we can imagine a right triangle. So let's suppose this is a right triangle, and this is an angle x. So if cosine of x is equal to 1/4, that means that this side, the adjacent, is 1, and the hypotenuse is 4. And then we can use the Pythagorean theorem to find this other side, which we'll call b. Now notice that from Pythagoras, we know that b squared plus 1 squared is equal to 4 squared. Therefore, b squared is equal to 16 minus 1, and then this implies that b squared is equal to 15. And then b is equal to plus minus square root of 15. But Notice that that says that x is between 0 and pi halves, which is the first quadrant. So we're going to be dealing with positive values only. Okay, so that means that this is equal to, or b is equal to, the square root of 15. So that's going to be this side here, square root of 15. And then, using the fact that sine of x has to equal opposite over hypotenuse, that means that sine of x is equal to the square root of 15 divided by 4. Now the other method is using the trigonometric identity that says sine squared of x, and this is from the Pythagorean identities, sine squared of x is equal to 1 minus cosine squared of x. So if we substitute, we know that sine squared of x is equal to 1 minus 1/4 squared, and then sine of x squared is equal to 1 minus 1 over 16, and this is equal to 15 over 16. Square root both sides, and we know that sine of x is equal to the square root of 15 over 4. And the solution is positive because we're dealing with the first quadrant. And for part B, all we have to do is use the double angle identity. We know that sine of 2x is equal to 2 times sine of x times cosine of x. So we simply substitute, and this is going to equal 2 times 15, square root of 15 over 4 times 1/4, and this is going to give us square root of 15 over 8.